Did you know that, according to the IEA, the International Energy Agency, AI optimized data centers will consume over 68 gigawatts of power by 2027? Yeah, that's a lot of power. But, folks, we can make this better. How exactly? With the choice of connectors we use. Hi, I'm Amelia Dalton, host of Jock Talk. AI data centers require substantial power, and the global demand for power for AI data centers will only increase in the coming years. In this episode of Chalk Talk, Donald Harper and Mark Farrelly from Amphenol join me to discuss the biggest design trends in data servers and storage applications, and why your choice of a connector can make all the difference when it comes to power and performance of your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Amphenol. Hi, Donald. Thank you so much for joining me.
Thank you, Amelia, and we're looking forward to all of our people out there who use Mouser products and Amphenol products as well.
Excellent. And thank you for joining me, Mark.
Hi, Amelia. Thanks for having me. Happy to be here.
Excellent. Okay, so we're talking about artificial intelligence today, but in order to talk about AI, Mark, we also need to talk about the sheer amount of power that AI demands, right?
Yeah, that's exactly right, Amelia. The modern AI workloads, especially those powering the large language models and advanced simulations, really demand unprecedented computational power. So that translates directly into increased power consumption in the data centers. And think about it, even a single high end GPU draws hundreds of watts, and these systems often run thousands concurrently. So to support that, we're seeing a shift towards higher current infrastructure requiring robust interconnect solutions. And the scale of power consumption moves the power needs of a single data center from hundreds of megawatts to even a projected gigawatt for even a single facility. So it's massive, a 10-time increase in only the last few years. For reference, a typical traditional nuclear reactor produces about a gigawatt of power. So for us here at Amphenol, this creates a critical need for efficient, high power delivery, pushing interconnect technology to its limits, and ultimately pushes us to expand those limits to handle those requirements.
All right, so Mark, what specific areas are we talking about today?
Yeah, so I'd like to sort of give you a bird's eye view of a modern data center. And what's evident immediately here is the sheer complexity. You got everything from gen sets outside of the building, all the way through transformers, switchgear, UPS, HVAC, and then right into the racks and the servers themselves. So what we do at Amphenol Industrial, as you can see from these callouts, is provide the vast array of connector solutions for every one of these submarkets. And oftentimes we've been able to take ruggedized connectors and interconnect solutions, which were designed for harsh environments, potentially in different markets, very different markets, and utilize them for the high current solutions needed for power generation, storage, delivery, and everything in between. But today, rather than go through everything, we're going to zoom in and focus on the heart of the data center, the power delivery directly to the printed circuit boards within the servers, and the power distribution to the racks themselves. These are the areas where efficiency and reliability are absolutely critical, especially with the power demands of AI. So we'll be discussing how Amphenol Solutions addresses the unique challenges of this part of the data center where space is tight and every watt counts.
All right, Mark, so what Amphenol solutions would you suggest for these systems?
Yeah, sure. So let's start by breaking down this slide here. This illustrates the typical power distribution backbone in a modern AI driven data center. On the left side, you see the overhead track busway, and you can think of that as kind of the main power artery delivering the high capacity electrical current throughout the facility. It's a critical piece of the infrastructure, especially with the increased power demands that we talked about for the AI workloads. Now, to get that power down to the racks themselves, the tap-off boxes are essentially an access point along the busway, allowing us to draw off the necessary power for each rack. And that's where interconnect becomes absolutely critical. You can see our IP&S, or industrial pin and sleeve power whips, the plugs or receptacles, which we call the Ampha 309. These are the connections that bridge the gap between the tap boxes and the rack level power distribution units, or the PDUs. So in AI-driven data centers, these connections are handling significantly higher currents than we've seen in the past. We need to provide robust, high current connections that withstand the demanding conditions of these power-hungry systems. So why is it important? Well, as you can guess, with AI, power fluctuations or any interruptions can have really catastrophic impact on their performance. A single faulty connection can bring down the entire rack, disrupting the whole AI processing. So that's why high quality interconnect solutions like the Amphenol solutions, specifically the Ampha 309 in this case, are essential. These rugged high current connectors are designed to handle the consistent power requirements of today's AI infrastructure.
All right. So give me some more details about these solutions. What about the Amphenol 309?
Yeah, it might help to just take a step back. So, when we talk about heavy duty electrical connections in industrial settings, you'll hear terms like pin and sleeve and IEC 60309. So, you can think of the pin and sleeve as a general category, describes connections designed for tough environments where pins on a plug fit into sleeves on a receptacle, so ensuring a strong, reliable connection. Now, the IEC 60309 is a specific international standard within that category. So it's crucial because it standardizes the dimensions, the configurations, and pretty crucially, the color coding of these connectors. This standardization is all about safety and compatibility. So imagine if you were able to plug a high voltage appliance, say, into a low voltage outlet. That would be obviously a recipe for disaster. So the IEC 60309 standard prevents that. The color coding lets you instantly see the voltage rating, and the individual designs for each voltage ensure that different voltages simply won't fit together. So while all IEC 60309 connectors are considered pin and sleeve, not all the pin and sleeve connectors meet this standard. IEC 60309 connectors are very common in many industries outside of the data center applications that we're focused on today, but basically anywhere where ruggedness is essential. In the US, we primarily follow the National Electric Code, or NEC, so we build them to meet both the IEC and the US safety standards, which include UL 1682 and 1686. So it's about essentially ensuring that power connections are robust, reliable, and most importantly, safe wherever these used. These Amphenol 309s are available from as low as 16 amps all the way up to 125 amps, but mostly we're seeing applications at and above 60 amps in the latest tap boxes and PDU designs with voltages up to 690 volts.
So, what about the GTR solution?
Sure. So the IEC 60309 connectors are also kind of chunky. So in data center, space is at a premium. So every square inch counts. You can imagine if we could get the same high current capacity, safe reliability, but in a much smaller connector, it would be pretty useful. Why? First, the density. Smaller connectors mean more power outlets in each rack, allowing for higher density server deployments. That translates to more computing power per square foot, which is huge for efficiency and cost savings. And second, the GTR plugs and receptacles are much easier to handle and connect to each other, given the small form factor. The third thing is the flexibility. Smaller connectors can be easier to route and manage, especially in tight spaces. Really, once again, comes down to the patented RadSock contact technology. It's about maximizing the power capacity while minimizing the physical footprint. So Amphenol's core RadSock technology employs a hyperbolic grid socket, translates into significant increase in contact surface area, resulting in higher current capacity within a compact form factor. So with the GTR, it's capable of up to 120 amps, and it's about half the size of a 60309 connector. So essentially, a smaller, higher current connector allows data centers, specifically the busway, tap boxes, and PDUs, to achieve the same power delivery in a less bulk, leading to higher density and greater flexibility. It's about doing more in less space, which is exactly what the data centers are striving for.
Absolutely. So, what about the PRB solution? What kind of features are we talking about here?
Yeah, the Ampha PRB connector, it gets even smaller. So what's impressive is the compact design. In fact, this receptacle fits within a single rack unit, which is under 1.75 inches, and yet it's still capable of handling up to 60 amps. Think about that, 60 amps in just a 1U form factor. And that's important because in a data center, every inch counts, right? And the PRB enables broader and even more dense PDU configurations. Typically, the only way to connect up to a 60 amp connector to a 1U PDU would be to use a power whip through a cable gland. It works, but there's plenty of applications where a cord hanging off the PDU isn't desirable or limits other performance or logistical characteristics. The PRB receptacle provides a clean and compact interface directly on the surface of the 1U PDU or any other rack-mounted device. It's TUV and UL certified, it's touch safe with a IP67 rating, and it's very cost-effective compared to other connectors. It's been widely used actually in solar and other industrial outdoor applications for many years, and we're really excited to see that it's becoming a first choice for data center applications now as well.
Cool. Now, Mark, what about the Amphi Mini PD? Can we also talk about the benefits these connectors bring to the table?
Yeah, sure. We'll switch now to power to the board applications. So the Amphenol's Mini PD and Mini TD PD2 connectors are specifically relevant for these PCBA connections for high power GPUs designed for AI. This connector line's built around, again, Amphenol's core RadSock contact technology, which employs a hyperbolic grid socket in the contact surface area, resulting in higher current capacity and a compact, shorter form factor. So in this application, we're typically talking about 70 amps to 120 amps with voltages up to 1500 volts. So for those of you out there designing high density boards, obviously space is at a premium and these connectors help maximize that real estate. So it translates directly to more efficient layouts and potentially even smaller boards. The Mini PD and PD2 include an integrated latching mechanism, which is a critical aspect for reliability, especially in the demanding AI environments. And the industry trends towards ultrasonic welding is also an important factor. These contacts are available in both ultrasonic and traditional crimping configurations. They're available in swage terminations for bus bars and soldering pins for direct PCB mounting. Connectors offer low insertion force and maintain the higher current capacity that our customers are used to thanks to Amphenol's RadSock technology. The combination makes them ideal for applications for frequent mating and unmating without sacrificing any power delivery. Available in 5.7 millimeter and 6 millimeter sizes, with the 6 millimeter supporting up to 120 amps. These housings are available in PBT or LCP materials, LCP being for a higher temperature. They're both UL certified. And just to summarize, I'd say Mini PD and PD2 series offers high power to board connectivity and reliability in a very compact package.
So, Mark, we should also talk about the RAD-Z solution as well, right?
Yeah, that's right. Our newest innovation for these power-hungry processors is the RAD-Z series. So the RAD-Z line is also built around Amphenol's core RadSock technology. And we'll break down the key advantages on this connector, incorporating these latest innovations. So the enhanced compact design. So we've further refined the RAD-Z series with a new, even more compact design, includes improved latching mechanism, that not only enhances connection reliability, but also contributes to the increased space efficiency. So this is particularly useful for applications maybe where vibration, shock, or thermal cycling are factors. And then high current density, the increased surface area inherent to the RadSock, which allows for higher current capacities from 120 amps, and in this case, up to 200 amps. Again, we're talking about delivering significant power in a very small footprint, and it's crucial for applications where board space or enclosure volumes at a premium, such as high performance computing. So it's important to note too that the RAD-Z series utilizes ultrasonic welding. So this ensures a robust, low contact resistance connection, critical for maintaining signal integrity and reduces any power loss. Also, we'd like to note that the geographic diversity and supply chain security on this product. So to meet the demands of many of the hyperscalers we talk to, ensure the supply chain resilience, we manufacture the RAD-Z connectors in both Endicott, New York, and in Zhuhai, China factories. So the Amphenol has also cross-licensed this technology with Molex, so providing multiple sourcing options, which is often also mandated by some of our larger customers. The dual 8 millimeter RadSock contacts are configured in the RAD-Z cable assemblies with either 2-gauge cable, one 4-gauge cable, or two 4-gauge cable. In essence, RAD-Z is about just delivering power in a compact package using proven RADSOC technology and added enhancements for reliability, space efficiency, and it also delivers that supply chain robustness.
So, Mark, are there any other solutions we should talk about for these kinds of applications?
Yeah, we're excited about another product or a solution for delivering the high power directly to the PCBs. So those are found in AI servers, of course, and we generally refer to this category of product as our RAD-cert connectors, built on RADSOC technology. And these connectors offer exceptional current carrying capacity with low insertion force. So specifically, today we're going to talk about the GMT floating RAD-cert, which is short for gross misalignment tolerance, a GMT. This version of the RAD-cert addresses a common challenge, right? Misalignment during mating. And the floating feature of this connector allows it to accommodate variations, ensuring a reliable connection even in a blind mate scenario. So this is crucial for board-to-board and bus-bar-to-board connections, where tolerance stack-up is likely to become a concern. The GMT RAD-cert can accommodate up to a millimeter radial float. The GMT RAD-cert can accommodate up to a 1 millimeter radial float, which is actually quite large acceptance range. The GMT RAD-cert is available from 3.6 up to 18 millimeters, which is potentially capable of actually over 1,000 amps of current carry capacity, which is pretty impressive. So these GMTs are used all over AI data centers with their power-hungry GPUs, but are also used in all kinds of big industrial applications that require a lot of power. So I also want to point out that the floating mechanism feature itself and so much of the technology of the RADSOC is on the socket side of the system, but the pins are also very important. So we offer solid copper machine pins, which are available in a wide range of length, plating options, and for certain applications, other copper alloy materials as well. So that wraps up the Amphenol industrial part of this Chalk Talk, which I hope highlighted Amphenol solutions to address the unique challenges of the power to the rack and power to the board applications in AI-driven data centers.
Fantastic. Now, Donald, when it comes to data servers and storage applications, what are some design trends we should keep in mind?
Yes, thank you. So Mark did a great job kind of presenting the data center picture and how much power is required. My expertise is in the server and storage applications. I'll show you some of those applications. But in a general sense, what we see going on with AI, and certainly last year was an explosion of AI in our customers designing AI systems. And now we're living in this new world where it's more and more required for our systems to go even faster. So while we supported our customers releasing Gen 5 products, we're now working on Gen 6 products to get even faster data rates. What comes along with this, and Mark kind of alluded to this, is with more power, this also introduces more of thermal challenges in the card or the rack or even in like these systems. So our connectors are having to perform with even more power added to them, and you'll see that as we have expanded some of our product lines. The other thing that is a trend right now is to get things as close as possible in the server and storage area, to get these components as close as possible, to limit the signal losses and maximize the speeds that these things can run at.
Fantastic. All right. So, the SSIO business unit at Amphenol would be a good fit for these kinds of designs, right?
Yeah, so what you can see here is a 1U blade, and this looks like a compute blade or a server blade. But what makes this business unit unique is we capture all the products that have to do with memory that are inside of a server or a storage box. And what you can see is a list of all these things and kind of how they're shown in a typical application. And I'll kind of walk through them just to give you an idea. But what's driving this is, like we said, faster speeds, shorter speeds. So if we go around this picture here, we look at the M.2 has been one of the oldest memory connectors in every system. For years and years have had M.2 connectors, and they've gone through multiple generations. And now we have our Gen 5 M.2 that you can get through distribution. And they come in all kinds of configurations. The most standard configuration, though, is the right angle at different heights. And you'll see that we have those products available. The next one that I wanted to highlight is our mini cool edge. So all these products are card edge type of applications, meaning there's a receptacle on the connector side, and then what plugs into it is some kind of a PCB board with gold pads on it that mate to the connector. Our mini cool edge product family is designed specifically to run at the fastest speeds we can get. We have right now Gen 6 products. But what else is unique about this is we're combining power right into the connectors that have all the high-speed signals. And so these connectors are expanding to be able to provide custom solutions, as well as there are some standard solutions. And I should probably talk about standards right now too, because what you see right here, all of these connectors align with some kind of a standard. This specific application of a server and storage for years and years have created standards so that multiple suppliers can provide solutions, and they all can work together with common cards and SSDs and things like that. So what Amphenol does really well is we have a department that has nothing to do but work on standards. So they're involved in standards and the newest standards that are coming, and we support all those with a whole team of people that participate in the standards. And what that does for Amphenol is it gives us this leadership position that comes through a standard, especially for next generation product, where we typically know what that next generation product is, and we like to be on the cutting edge of tooling up these products. And certainly we go through the signal integrity simulation work on all of these to come up with our next generation products. And you wouldn't believe how sophisticated these products are getting. Internal shields, special materials, and now maybe one of the latest trends is high-speed cables. It's most desirable to run your highest speed cables as close to the processing units as possible, but there's only so much space and they're packing lots of memory in here. So one solution you'll see is a cableized version of a lot of these connectors. So if I move to the next category, it's the EDSF connectors and cables. EDSF is actually a standard. It's an SFFTA 1002 standard. And that defines the mating interface and sometimes the performance of these connectors. What the EDSFF product family is, though, is a set of standard sizes with different orientations. So what you can see here is an orthogonal orientation where an SSD might plug straight in through the front of the blade into this connector to be able to connect into the motherboard. And these come in various sizes that are part of the standard, a 56 position, 84 position, 140 position, and there's some other special ones added. And we typically tool these things up first in a vertical orientation, then in whatever the customer or the application demands. But the vertical is the most simple one for electrical reasons and just mechanical reasons as well. We have already tooled up all the Gen 5 EDSF products in a vertical, right angle, straddle mount, and orthogonal orientations. And you can see here there's an orthogonal cable, basically just pulls all the signals out of whatever's getting plugged into the front. In this case, this is an SSD standard. So this covers the SSDs for an E1 and an E3, and all these things may be familiar with you, but these are the standards that define the SSDs interfaces. And we have all these products in Gen 5, and we have some about our Gen 6 products. Moving on to the U.2 section, which is around the side. The U.2 is a connector family that has been an extension of the SAS and SATA formats. Standard spec is the SFF 8639. If you're in this space, this will make a lot of sense. If not, it's just a standard that defines the mating interface. And the U.2 continues to promote this SAS-SATA contact structure. This is a two-piece connector system, meaning on your blade or server will be a receptacle. And then we have customers that make SSDs and HDDs. They will put a plug contact on their product, and that typically gets plugged into a storage box. What's important to our customer is being able to provide a transition to a next generation performance with as much ease as possible. So when we design our next generation products, you'll see how they connect to the board the same, so that when you're ready to do your next generation system, you can remove this connector and on your new layout, use the same exact footprint. And that's been really successful for our Mini Cool Edge, for the EDSFF, for the M.2, and most of these products, this is the case. The step from Gen 5 to Gen 6 was a smaller step than I think we realized. Our Gen 5 products were so close to achieving Gen 6 performance that as we've designed now the Gen 6 products, most of them are footprint compatible, meaning they can drop right in where a previous generation connector was. So DDR has been around for a very long time, and it is another memory solution that right now has the most memory capacity, and that's why you see in this picture all these DDR sockets are stacked up right next to the processors so that they can do these large language models that run in and out of memory to do calculations. And so where DDR5 is going is, I have a slide to talk about this. It's a new format is coming out called CAM, and where it will lead in the future is still not clear. So I'll show you a little bit of what CAM looks like and talk about DDR5 in a little more detail. The last group of card edge products that the SSIO business unit produces is the PCIe product family. This was the first product that came out to mate to a card edge. And likely you've had PCIe cards for many different things, graphics, processors, and you'll find these in every system. A card, a PCIe card gets plugged in to do some additional function, and every system uses PCIe cards. We right now have our Gen 5 product completely tooled in every different size, lots of configurations, and even a cabled version that you can put on a board, plug your PCIe card in, and run your signals right over next to the processors or wherever you want to function those signals. All right, let me talk about a success story that we have at Mouser.
Okay, let's get into it.
So what I hear as I get out and meet with customers is, because of this AI future thing that's going on in the world, all of the industry now is looking at this as an opportunity to come out with their own AI solutions. So where our product has been focused on the server and storage applications, what we're seeing now is all these applications are going into the server systems, but it's created a flood of other customers in the robotics area, in the industrial area, and in the medical area, where they have a card that's going to get plugged in, but they now want to start coming up with products that introduce AI functions. And so they're looking for us to be able to supply the fastest products out there. And for these smaller customers, it's ideal for them to be able to get these things quickly, to go through distribution and customers. And what I'm showing on this slide is one of our products that's been very successful through Mouser is the PCIe Gen5 product. What I ask our group to do is put together some numbers that just show what kind of products are going through distribution. And as you can see, lots and lots of sales and lots of products are going through distribution at Mouser. Here's a couple of those in this specific application. So for the PCIe product, I didn't go into much detail, but we have a bunch of different variations of that. We have a narrow footprint that allows you to put more of these closer together. We have another version called the Flip Chem, and it's a unique design for how the PCIe connector attaches to the printed circuit board. So in a traditional surface mount connector, all the leads would go outward so that they could get routed out through the outside of the connector. But if a customer wanted to save some space and get a connector as close to the board as possible, one way to do that is to change the surface mount solder leads to a JJ configuration. And this would make sense if you can see the connector. But basically, leads don't go out on the sides, but one of them turns inside, and that allows you to get this as close to an edge and route things out through the inside of the connector. The point I think that we are trying to make at this is with all of our customers needing PCIe, we have the Gen 4s. Last year, we tooled up all of our Gen 5 products as the AI industry was exploding. And we're seeing lots and lots of people come to Mouser for the server and storage products because we know that they're standards. We know that they're in all of these boxes, and so it's a great place to start, either at our website or at the Mouser website. We have all the server and storage products for you to take a look at and try to get as quickly as possible.
All right, so Donald, can we take a closer look at the Gen 6 connector family?
Yes, thanks so much. I mean, this is where all of our engineering work and our support work with customers is happening right now. It is with the folks who are designing the server and storage applications. Right now, they've released their Gen 5 systems and product, and they're already building their Gen 6 because they know how critical the performance is. And so, for the different categories that I was just talking about and showing you, let me show you what we have already tooled up for Gen 6. This is allowing our customers to get a head start. Not all the customers of all of our competition has tooled up Gen 6 products, and everybody's kind of rushing to do that. But I'll show you here on this slide, it talks about what we have available. So part of the card edge products do take memory, but a lot of them are just plug-in riser boards or host boards. What we have for those is typically a vertical connector that you can see in this picture. The DDR5 is available, and I'm going to talk to you about DDR6. For high-speed board-to-board, our Mini Coolidge, which is a product family I'll talk about in a little more detail, we have already tooled up Gen 6 products, and with this good news that they're footprint compatible. So the customers that are using Gen 5 are not quite ready to be at the Gen 6 speeds. They can use their Gen 5 or take their system and be ready to move to Gen 6 for all their Mini Coolidge board-to-board applications. The other area that we're doing this is kind of support the SSDs. So all these host cards are in some form a card that's plugging into a receptacle. And that's the same case for a vertical and right angle Gen Zs. These are standards that we already have tooled and are ready. Another one on this list here under the host board card edge is a PMM. And I have a slide on this. It's basically a version of this that we're adding additional power that's becoming more and more needed in this. I want to highlight down at the SSD form factors, and you can see our riser cards as well. For the SSD form factors, they come in 3 different kind of standards. There's the SAS SATA, right now kind of nicknamed the U.2, but it's the SFF 8639. These are SSD form factors I mentioned, the E1, the E3. There's an E2 that's actually moving into standards right now. We have the Gen 5 products tooled, so you can get those online. Our Gen 6 connectors, we are right now going through tooling up the Gen 6. We have a Gen 6 receptacle, and in the next couple of months, we'll have the Gen 6 plug as well. And plus, when we do that, we typically have all the signal integrity models, all the CAD models, the drawings, everything you need is certainly on our website, and Mouser typically will carry them over into their website. So if you're thinking of the SSD form factors for the SAS and SATA or PCIe signaling, this is one of the standards that is being used pretty frequently for SSDs. The other standard in the SSD format is a EDSFF standard, and that is something I talked about before, but What's nice to be able to see in this picture here is we show it in a vertical orientation and we show it in the orthogonal orientation. And this should hopefully give you some idea of how these SSDs would plug into your board or your card. You can either mount a card vertical or you can have it in an orthogonal orientation, which is the most popular version of this. For this specific standard, we have tooled up the vertical in 4 different sizes for Gen 6. That's ready and available. We have customers using it in systems right now. For the right angle, it's coming along as well. We have that in the 1C, 2C, and 4C. And when I say that, 1C, 2C, that references the standard, but it's a number of contacts, 56, 84, or 140 positions is what that's referencing, the 1C. Also for the M.2 product family, we have tooled up a Gen 6 product and it's still in an evaluation stage. I don't think that it's probably available through distribution, but if it's something that you're integrating into your system, we can provide that as well. And let's talk a little bit more about the generic card edge connectors.
Okay, so let's do that. Now, when it comes to these card edge connectors, what does Amphenol offer here?
Yeah, the reason I like this chart is it helps you get an overview of what all these products look like and what differentiates them. So across the top of this chart is the pitch of the contact. How much space is there from contact to contact? And if you look over on the right-hand side, what you see is the PCIe connector family is a 1 millimeter pitch connector. So as time has gone by, our customers have wanted to get more and more contacts into smaller and smaller space. And so as you move from right to the left, what you see is the first card edge product family, the PCIe, that was at 1 millimeter pitch, comes out. Next, the DDR product family at 0.85 millimeter pitch. And then Amphenol started leveraging this card edge design and moving it down into higher densities or smaller pitches. So we have our product family that we call Cool Edge, and it comes in various different pitches. The standard Cool Edge is at 0.8. It integrates power. It has a lot of flexibility. For this product, we have our product tooled in a modular fashion so that we can come up with so many custom versions for the number of signals, the number of power you want to integrate into your solution. That same carries over into our Slim Cool Edge product family at 0.65 millimeter pitch. And then what I was just talking to you about was the EDSFF standard, and that is a 0.6 millimeter pitch. And we call it our Mini Cool Edge product family, but it supports a bunch of different standards. Certainly the biggest one is the SSF 1002. That's the SSD standard that is in every system out there. And I'm sure you're hearing in these data centers, they're just getting as much memory in there as possible. It's just a gigantic warehouse full of hard drives, SSD drives, and all of those get connected through this EDSFF standard we call Mini Cool Edge. There is another standard that came out and hasn't been adopted too much, but we have tooled it up. It's Micro Cool Edge. It's on a 0.5 millimeter pitch, and we have it in an orthogonal configuration. But the 0.5 millimeter pitch is the pitch that the M.2 connector is on. So right now, the M.2 is the most dense card edge product that we have in our family. So we see a continuation of M.2 going on as we continue to provide solutions into the artificial intelligence category. The last group there is a product family called Double Density Cool Edge or Double Density Card Edge. And I don't have a slide to show this, so let me try and give you a picture. Where the card edge has gold fingers on, for the double density, there's 2 rows of gold fingers on the card. So there's 2 sets of contacts, one that passes over to the second level and one that touches on the first set of gold pads. In a way, this gives us this opportunity to have our contacts on a 0.4 millimeter equivalent pitch. The contacts themselves are spaced out on 0.8 millimeter pitch, but because of the double row, we can get double the contacts in there. That is really taking off. People are finding where they need that extra density. They really like that. And what I want you to really just walk away with this is the evolution of the card edge family moved from 1 millimeter pitch down to 0.5 millimeter pitch. While we do have connectors that are down at 0.4, 0.3, the card edge right now is limited to the 0.5 millimeter pitches, the tightest pitch we have.
Fantastic. Now, Donald, I think you mentioned the mini CE PCIe Gen 6 as well. So, can we talk about that a bit?
Yeah, so I have a slide here to try and just give you some picture of what the electrical performance looks like for this. And as you could imagine, the Gen 6 signal speeds that continue to get harder and harder. Gen 5 was 32 gigs, Gen 6 is 64 gigs. We do have a Gen 7 solution that we're working on now, but the Gen 6 is available right now. And I mentioned this too earlier that this is the exact same footprint to the Gen 5 product. So if you're using Gen 5 or even likely the Gen 4 product, you can move to the next generation of performance with the Gen 5 products because it's footprint compatible. And when we typically release a product, because we're tooling up the contact design as a solution, we can mold different sizes of housings and just make it different sizes of connectors. So this is already tooled up in the 56, the 84, and 140 position, plus one version with extra power, the 4C plus. And when you pin these things out to run high-speed grounds, what you can see is we have addressed the crosstalk, which is the biggest issue, to be able to maintain the intermatability form factor that a card for the EDSF standard can plug into this from any supplier to keep that mating interface, the standard configuration that's defined by the EDSFF standard. And I'm not an electrical engineer. I hope this is meaningful for some people. But as you can see, we projected out Gen 6 requirements, and we can meet those already.
Fantastic. So, Donald, if my audience needs a PMM connector, what would you suggest in this case?
I'm sure that your audience definitely needs this because the way this came about was the industry came to us or came to the standards organization and said, we really like all these card edge connectors, but we can't get enough power through them. So we need a way to get increased power running through this. So this is a pretty new standard. It's the SFFTA 1037. And it builds on the mini cool edge. We call it the hyper cool edge at 0.6 millimeter pitch. So it takes our standard card edge technology and adds some power contacts in there, a little bit bigger that can carry more current. And we specifically tailor this to align to what we're finding is the requirements for power inside these boxes. This is going to be some kind of an add-in card where you need to get the signals and the power into maybe your motherboard or a larger card, because this is designed at its maximum potential to be able to carry 600 watts. These pins enhance the power from 200 watts up to 600 watts, and it's crazy that there's so much power going on, but that's what this AI industry is driving.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Donald.
Thank you.
And thank you for joining me, Mark.
Thank you. Appreciate it.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Amphenol. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.